Well, hello there. I'm Venkatesh. Today's topic is uniform convergence continuity theorem and its related problems. So let us see what is. Let's see the basics to that theorem. If we take that theorem, the basics of that theorem will be uniform convergent definition. We have to understand uniform convergent definition. So let's directly see what's uniform convergent. Uh, a sequence of function fn of x is said to be uniform convergent to a function f of x on a if for any epsilon greater than 0. We are taking epsilon greater than 0 here, um, where m is a positive integer depending on epsilon, such that mod fn of x minus f of x is less than epsilon for all n greater than or equal to m, where x belongs to a. Here, you know, epsilon is a very small number. I have Let's see what exactly this. It can be written in this form. Is it? We can write this as. We can write this as. Let's write it down once again. Epsilon less than fn of x minus f of x less than epsilon. We can write this as f of x minus epsilon f of x plus epsilon. We are just operating f of x on all the sides. So visible, yeah, it's visible. So we are writing this, we are just taking away the mod here. After taking the mod, we get in this form. After that, we are operating f of x on all sides, so we get in this form. That means that, uh, let me show in a diagram. Yep, visible. So f n of x lies between f of x minus epsilon and f of x plus epsilon. That is, let's take this as fn of x. It lies between f of x plus epsilon and f of x minus epsilon. So fn of x will lie between these two. If this is true, then the given function sequence of function is uniformly convergent. So this is all about uniform convergent definition. Let's dive to the theorem. Uniform convergence and continuity theorem. Basically this is my topic, and let's see what statement says. If fn of if fn is uniform, is the sequence of your continuous function on closed interval a comma b, and if fn converges to f uniformly on closed interval a comma b, then f is continuous. uh, Basically the statement says, I will just explain it. Statement of theorem actually says is, when fn is continuous, when fn the statement says that fn is continuous function on closed interval a comma b if fn converges to f. This is convergence sign, uniformly. We can write this as uniformly in this way. If we write this, it means that it is uniformly convergent on closed interval a comma b, then f is continuous. So we are proving this now. Then we are solving related problems to it. So let's see how the theorem works. See the proof. Let is greater than 0 be given, and since Fn is uniformly convergent by the given statement here, uniformly convergent on F, there exists positive integer m such that Fn of x minus f of x is less than epsilon by 3 for all. We are taking this for all n is greater than or equal to m, for all x belongs to closed interval a comma b. We are just taking this, we are taking epsilon by 3 so that we can solve the proof in a easier way. So let's take another point. Let's take it as a, let it be c. C be any point, C be any point of closed interval a comma b, then equation 1 we have, from this equation we get that Fn of c, we can see this, Fn of c minus f of c module n is less than 1, and for all n is greater than or equal to m. Since we know that Fn of since we, I'll write it down, since f of n is continuous, on a comma b, therefore c belongs to closed interval a comma b is Fn is also continuous. From the definition of uniformly continuous, we can say that you know delta is dependent on epsilon, or we have taken in our classes as neta. It can be delta is dependent on neta or epsilon, which is same. If that is true, then it is a uniformly continuous function. So let's write it as is greater than 0 such that Fn of x minus f c mod, oh I think it did not, okay. So from the definition we are taking as is greater than 0 such that mod Fn of x minus Fn of c is less than epsilon by 3 whenever x minus c is less than delta. So what we are doing is we are operating Fn of x and Fn of c, we are just adding it and subtracting it to this equation. So we get Fn of x minus f of c now. Yeah, we can see that oh, it was playing. Now we can see that we are just adding and subtracting Fn of x and uh, f of c here. So we get inequality f of x minus Fn of x mod plus mod Fn of x minus Fn of c plus mod fn of c minus f of c. So as from equation 1 and equation from this equation we can write all this as epsilon by 3 this, and this as you can see here epsilon by 3 and epsilon by 3. So whenever six is less than 0, f of x is continuous. At a point c belongs to closed interval a comma b. Let us see once again. What we are doing is we are taking an f of n as a sequence of continuous function on a comma b. So we are proving it f is continuous on a comma b, on a closed interval a comma b. So here is a note on which is related to our problems in which we are taking next. I will say it one. I will just explain it. Uniform convergence of a sequence of f of n is only sufficient condition but not a necessary condition for the continuity of the limit point f. That is, the limit point of f is continuous on closed interval a comma b. It is not necessary that the sequence fn is continuous, is uniformly convergent on that interval a comma b, that is closed interval. If the limit function f is discontinuous, then fn cannot be uniformly convergent. It's true. As you know, the limit function f is discontinuous, then sequence fn cannot be uniformly convergent. This is very much important for us in the next upcoming problems. And if fn of x is a sequence of continuous function on an closed interval a comma b, then f of x is discontinuous function of pointwise limit, then fn of x is not uniformly convergent to f of x on a comma b. So here is some of the notes which which is helpful for solving our problems. Let's take the problems one by one. The first problem, fn of x is equal to tan inverse n of x, where x belongs to closed interval a comma b. Let's find this as a is it an uniformly convergent sequence on this given interval a 0 comma 1. Let's see. Now let's take pointwise limit. Let's take for 0, let's take x is equal to 0 first. When x is equal to 0, if we apply here tan inverse 0 is nothing but 0. Then if we in a given interval is closed interval from 0 to 1, it can be written as limit n tends to infinity. We can see many numbers here, so let's take it as tan inverse nx, the given solution, I mean given problem. So if we apply limit to it, then we get tan inverse infinity, which is nothing but pi by 2. So if we apply x is equal to interval 0 comma 1, we get pi by 2. We can see it is not uniformly convergent. It is not. uniformly convergent. Here it represents to tan inverse of x here, to be precise, on 0 comma 1 interval. I think it's visible now. I will say I will go fastly now. Uh, we have to prove that the given fn of x, that is tan inverse of nx, is convergent. So by doing pointwise limit, we get that the limit is closed interval 0 comma 1. If we apply that, we get when x is equal to 0, it's 0, but when we apply the limit here, we get pi by 2. Hence it is not uniformly convergent. Let's take up another problem, which is a second problem. Yes, here it is. Fn of here fn of x is equal to 1 by 1 plus n of x in once again the same limit, which is closed interval 0 comma 1. We solve this by pointwise. Once again, we have to do with pointwise limit itself to find whether the given function is uniformly convergent or not. So here f of x is equal to let's take let's take 0 first. X is equal to 0. When x is equal to 0, we get 1 here. And if we apply the limit 0 to 1, we get limit, we have infinity here, n tends to infinity, 1 by 1 plus n infinity. If we apply infinity here, we get, so we get it as 0. Hence if we apply the, we get 0. This is also a discontinuous function, hence it is not it is discontinuous, so it is not uniformly convergent. Therefore fn of x is not uniformly convergent on closed interval 0 comma 1. Let's take another problem. Fn of x power n on closed interval 0 comma 1. Once again, let's prove this by pointwise limit. Well, once again, we will take pointwise limit, which is let's take x is equal to 0 first. So if we take 0, we get 0. When we take x is equal to 0, we get 0. I hope it's visible. And if we apply the limit here 0 to 1, we get 0 to 1, we can take it as anything, which the number which lies between 0 to 1, that is well, n will tends to infinity itself. If we can take x as 1 by 2, 1 by 3, 1 by 4, anything, let's take it as 1 by 2 itself, to the power of n. If we apply infinity, we get 0. If I apply n tends to infinity, if we apply the limit, we get 0. Hence we get here 0 as well. If we take x is equal to 1, if we take x is equal to 1, but here we get 1. Hence we can say it is not continuous. We have discontinuous, uh, it's not uniformly convergent. We have discontinuous functions. So fn of x is not uniformly convergent on closed interval 0 comma 1. And if this one it was like on closed interval 0 and open interval 1, then it can be uniform convergent for this given function, given sequence. Here, as I previously mentioned, converse is not true. When f of x, when fx is continuous, uh, it is not true that fnx is continuous. It's not always true. But if fn of x is uniformly convergent, then f of x is continuous. So this is all about the topic here, and thanks for watching. Thank you a lot.